Hi everyone, it's week 3 in Business 2220. It's Instructor John here. This week we're going to do problem 3.23, which you can find in the textbook on page 134. It's the famous breaking trash bag case where we try to figure out how much stuff the trash bag can actually hold. Now, last week we learned how to take the strengths of these bags, and there are 40 of them. It's a sample of 40 that someone did, and create a histogram, the blue bars you see on the screen before you. And we can calculate some statistics about this. Rather than just looking at the shape of the curve, of the bars, we can say, well, let's do some calculations. Well, the most obvious thing to do is to calculate the average, the mean value of these 40 trash bags. And in fact, if we did that, we could calculate 50.575. To do that, of course, we add up all the breaking points, add them together, and divide by the number, which is 40, to get that average. Now that tells us where the middle of this curve is going to be, around 50, 50 and a half, thereabouts. But what is also of great interest to us as statisticians is the shape of the curve and its dispersion, how far it's spread out around that mean value. Well, life is very simple for a statistician if in fact the curve follows the normal distribution curve or the bell-shaped curve. Some people call it the Gaussian curve. Same thing, it's a bell-shaped curve. And you can see our data here. If you squint your eyes and look at it a little on an angle, it's pretty close to being a bell-shaped curve. So again, I keep telling you this, statistics is a judgment call in a lot of cases. It's an art and not just a science. And so we have to make a judgment as a statistician. Is this close enough to being a normal distribution or not? Well, we're going to eyeball it and say, yes, it is. Now, the standard deviation, as you probably know by now, having read in the book, you have read the book, haven't you, about standard deviation, is a measure of the dispersion. And it's really a simple calculation, almost as simple as the average. What we do is we take the breaking strength. I'm going to put a parenthesis around my little formula here. We're going to take the actual breaking strength of this particular sample and subtract from it the mean value, and that gives us a difference. Now, that would be interesting for you and me, but statisticians say, you know what's even more interesting, for reasons we won't go into here, is if we square that difference. Now, one thing that squaring the number does is to give us always gives us a positive number, no matter whether the actual trash bag is less than or equal to the average. You notice in this case, it happens to be greater than, it happens to be, the way I calculated it, to be 4 minus 50. Oh, I squared it already, didn't I? I'm sorry. I'm fooling myself. Let's look at it unsquared. Minus 2.1. Well, that's a negative number, and if we add them all up, it'll come close to 0. So let's square it the way the statisticians like to do. And then what we do is we simply make that calculation for all the strengths, all the sample values, and add them up. And divide by n and take the square root, and lo and behold, we get 1.6438. You can read about this in the book. I'm not going to do it here in the interest of time. So here's what we have. We have a curve, a histogram that looks pretty normal, and a calculation for the mean and a calculation of the standard deviation. Now, the book is asking us to do a calculation to answer a question. What percentage of the sample of all bags, if we were to take any random bag or a sample of random bags, assuming nothing changes, of course, what percentage of those bags would, I'm going to move this up a little bit so you can see the whole thing. What percentage of the bags would fall within one standard deviation of the mean? That is from 50 minus 1.64 to 50.57 plus 1.64. Well, the way the normal distribution curve works, the way the empirical rule works, we can be assured that 68.26% of all bags that we might sample in the future will fall in that range. So let's calculate that just for fun. So to do that, I'm going to write an Excel equation. It's going to be equal to, now what I'm going to do is take the mean, and I don't type in 50.575. That's too much work. And I want the lower limit, so I'm going to subtract one standard deviation, 1.6438. And that says the lower limit is 48.93. I'll do the same thing for the upper limit. Take the mean, add on one standard deviation, and I get 52.22. So the big news here this week, at least as far as the empirical rule is concerned, is that 68.26% of all trash bags that we might measure in the future will have a breaking strength that lies between 48.93 and 52.22 pounds. Now that's pretty useful stuff. If you're going to set an advertising campaign going, you want to be darn sure that the breaking strength that you advertise is accurate. Otherwise, the Federal Trade Commission, the state regulators, everybody's going to come down on you like a ton of bricks and say, hey, you're lying. Fix it. Okay, so let's calculate these other ranges. It's the same idea. Take the mean. This time we're going to subtract 2 standard deviations. Like that. And we're going to add 2 standard deviations equals that. You Excel jocks out there know that there's an easier way to do this, don't you? I'll show you a few tricks here in a minute. But for now, we'll do it the hard way. 2 times that. And the third one is equal to the mean plus 3 standard deviations. Oops, minus. You caught me. Thank you for paying attention. I'm glad you're watching here. It would have been a bad mistake. And equal to the mean plus 3 standard deviations. Okay, there's our table. So we could now say, depending on how confident, how wide we want this range to be, we can set limits. So if we really want to be 100%, almost 100% sure about the breaking strength, we can say with 99.73% certainty, the breaking strength will lie somewhere in the range of 45.64 and 53.58 pounds. All right, the textbook asks us next, does the estimate containing 99.73% of all breaking strengths provide evidence that almost any bag will exceed 45 pounds? Well, in fact, 99.73% of the time, the breaking strength will be 45.64 or greater. So yes, we're pretty confident of that. Now, oops, I've left the answers in here. I've been practicing. Let me take them out. Now, the next thing is to test this. Oh, I already had the numbers over here, didn't I? Let's test this empirical rule. I'm going to get rid of this so we can see what we're doing here. I kind of got messed up like this. Okay. Okay. Now, let's see how I'm doing for time. I'm doing fine. Okay. Now, the question is, I've simply repeated the range here for us. The question is, what percentage of the 40 trash bags that we had in our sample actually fall within the one standard deviation, 2 standard deviation, and 3 standard deviation ranges? That's a test of how good our theory is. We ought to have pretty close to 68% of these 40 bags fall within that range. Now, one way to do that is we could go in here and select all those numbers like that, and then come back up here and do data, sort, and let's sort that on strength. All right. So the smallest one was 46.8. So 48.93, 48.8. So those 1, 2, 3, 4. Those 6 values are less than our lower limit. We could go do the same thing for the upper limit, but you know, that's a lot of work. There's a command in Excel for this. You're not surprised, are you? It's called count. Not only count, but count if. Now, the first thing it asks for is the range. So the range is, come on down here. Here we go. Well, I'm in trouble getting my range to go. Hang on. Okay, here we are. There's the range. And then it asks for a criteria, a set of criteria, or in this case a criterion. We just need one. And the way you create these is you first put a quotation sign, and we want all values that are less than or equal to the lower limit. Oh, we're doing the upper, aren't we? Let's do the lower. I'll swap the things. The lower limit. So I close my parentheses and I put the and sign and say the lower limit is going to be 48. And I close that parentheses and I get 6, just like I counted by hand. Now I can do that for all three of these values, and the easy way to do that is to make sure I'm going to put some dollar signs in here. And what that does is say to Excel, when I replicate this cell, when I pull down on it, I want the numbers 42 and 81 to stay the same. So watch what happens. If I look at this cell, it's still A42 to A81, which is my range, but now my comparison is against C43. And the same thing here. The range stays the same, but the value of the C40X number has changed to be C44, which is what I want. I can take this same formula. I'm going to select it. I'm going to do copy. Home. Where's the copy thing? That's copy, isn't it? And I'm going to go over here and paste it right in there. But rather than have a minus sign, or rather a less than, I'm going to have, where's the greater than here? Greater than, there we go. Greater than or equal to. Whoops. Oh, I've got to change the reference, don't I, from C to D. So that says there's 7. And again, I've still got my dollar signs in here, so I can just pull down like that, okay? So what's that telling us? Well, it's giving us, it's saying there's 6 below the range and 7 above in this particular, in the one standard deviation case, or 13 in all. But really, we want to know how many are within the range, not how many are outside the range. So in my formula for count, I'm going to take 40 and subtract 6 plus 7. That says there are 27 within the range of 1 plus or minus 1 standard deviation. Now, let's make that, however, a percentage so that we can compare it to the empirical rule number. So we know that there are 40 values, so that's what we divide by. Woo! I did something wrong. Okay. Nag. I didn't put my divide sign in. There we go. Okay. So there's 6.75, or make that a percentage up here. 67.5% of the values are within 1 standard deviation. That's pretty close to 68.26. We can drag this down just like we've been doing. And we see that 95.0 compares to 95.44. 97.5 compares to 99.73. So we're doing pretty good. The empirical rule seems to be holding. That's because our curve was nice and bell-shaped. And that's all there is to this problem. But you can see the power of the first of all, having distributions that are normally distributed, have a bell-shaped curve, and therefore allow us to use the empirical rule. We can make some very quick judgments about this. So if your boss walked into your office and said, "Hey, John, someone went out and measured 40 bags. What can we set our advertising claim at? Tell me quick." The advertising agency's on the phone. You could, after you get the hang of this, you could very quickly come back and say, "Boss, we can be 99.73% confident that this baby will hold 45 pounds. No problem. Trust me." And your boss will say, "Hey, you're all right. How about considering a promotion?" Well, let's not get carried away. Okay, that's all for this week. Hope to see you online, and be sure to post those "I don't get it" questions. We're starting to get some good ones, and I enjoy having them. No question is too dumb, as they say, so post it, and we'll see what happens. Thanks. See you online.